Hey guys, welcome to our lesson for section 2.5, using exponential functions to model. We're going to talk about a couple different things here today with this lesson, and one of the first things we're going to talk about is growth and decay, which we already mentioned in the 2.3 video when we introduced exponential functions. We're going to redefine that. We're also going to talk about finding the growth rate and decay rate, and then we're going to talk about how we can use that with some real-world application problems to create exponential functions that will model them. And lastly, we're going to talk about, very briefly, using your calculator to do exponential regression on a data set. So let's first remind ourselves what an exponential function is. Very simply, any function that can be written as f of x, a, times b to the x. Remember, there are three restrictions on this. You should know them by now. We've talked about them a couple times. So I want you to pause the video, write those down. Welcome back from writing those down. Our restrictions are a cannot equal 0, b cannot equal 1, and b is greater than 0. Now with that restriction, the b value here is our base multiplier. It tells us how the function changes. And its value tells us whether we have an exponential growth function or an exponential decay function. And so if b is greater than 1, we have exponential growth, and our growth rate is equal to 1 minus, is equal to b minus 1. And then if 0 is less than b is less than 1, we have exponential decay. And our decay rate is equal to 1 minus b. Now, the reason why we treat them like this and consider them like this is because when we do that, we can treat them as a percentage change. And it makes it really nice and easy for us when we deal with these kind of word problems. And so what I want to do is I want to specifically go over a couple of kind of example functions and talk about how that would be interpreted as percentage change. And then we're going to go through some word problems and see how we can look at a percentage change in a word problem and apply that into a function. So, typically when we're talking about percentage change, we're talking about a function who uses an input of time. So as time passes, this thing changes by this percent. And so we want to use t to represent time. So instead of f of x, we're going to use f of t. And so let's say this equals 500 times 0.983 to the t. Let's say we've got a g of t, which is equal to 28 times 1.045 to the t. So both of these are exponential functions. We have an exponential decay function because our b value is between 0 and 1. And we have an exponential growth function because our b value is greater than 1. Now it's not greater than 1 by much, but it is still greater than 1. So since this is exponential decay, we can calculate the decay rate to be 1 minus b, or 0.983. And we get 0.017. Now, that's a decimal, right? And so I talked about wanting to convert these and talk about them as a percent change. And so the way that works is we want to convert this decimal into percent. And so that means that the decay rate for this is 1.7%. And we can even, further specify per unit time. So unit time just means like a single unit of that time. So if our time was years, then it'd be 1 year. If it was minute, it'd be 1 minute. If it was hours, 1 hour, and so forth. So whenever we say unit time like this, that means we're talking about a single one of whatever time it is we're dealing with. Now, what this is dealing with, what's happening here is so a way this could be worded would be something that starts with 500 of whatever it is, and every unit time, it decreases by 1.7%. Now, whenever we see that, we like to think, okay, so I want to put 1.7. I want to multiply this 500 by 1.7. But the reason why that goes wrong is because that tells us how much we lose in that first step. And then if we multiply by another 1.7, then that doesn't tell us how much we lose in the next step because it doesn't tell us how much we started with. And so what we actually are kind of doing here is we're saying if we lose 1.7% each time, that means we are retaining 98.3%. And so that's why our B value is 98.3, because every unit time, every step, we retain 98.3% of what we had before. And so instead of multiplying 500 times 0.017 and then subtracting that from 500 and then multiplying that result by 0.017 and subtracting it from that and so forth, that would work, because what that process is doing is finding what the loss is and subtracting it from what we originally had. Whereas this is saying, okay, every time we keep that much. So we're just going to find that much of what we had. And so that way it allows us to continuously do it very simply using an exponential function. We'll get to some more specific examples of how that works, and we'll do some more problem solving with that. Right here we have exponential growth. So that means our growth rate is simply 1.045 minus 1, 0.045, or 4.5%. So where does this 1 come from? Well, if you think about it, if I said, okay, you have, let's be really easy for ourselves, $100. Put it in a bank, don't touch it, you just leave it there, and it grows at 4.5% interest. What's going to happen after, say, a year is you'll have gained 4.5% of what you had. So one way that we can find that is we say, okay, well, I started with my $100 in there, but then I'm adding the 4.5% of that 100. So to find that, that's just 100 times 0.045. That's how we find 4.5% of 100. So we're looking at this and we're going, okay, that's what I've got. What we can actually do is we can kind of pull these out. And in doing so, we end up with this expression. And now, if you remember how to distribute, right, which is something that we're going to talk further about in chapter 4, but hopefully it's something that's not totally brand new to you. If we distribute this, we get 100 times 1, which is 100, and then 100 times 0.045, which is what we have right here. We can add these together and we get the 1.045. And so what this 1 kind of represents, it's like, okay, we keep 100% of what we have, and then we're adding an additional 4.5%. And so that's why we get 1.045, because if we were to convert that into percent, that would be 104.5%. In other words, every time we move 1 unit of time further, we keep 104.5% of what we started with before we move forward. So that's how those work. Understanding kind of how to do those is really important, but being able to interpret and go kind of from these to this is also really an important idea. So let's do a couple examples like that. So I'm going to give us 4 different examples. Hopefully I can fit them all on the board. I should be able to. And for each one of those, we want to create the exponential function that would model that situation. Okay, so example number 1. The initial value is $4,545, increasing 6% annually. The original amount is 132 grams. Decaying at 7.6% hourly. I'm running out of room there. We'll do these 2, then we'll do the next 2. So these are our 2 situations that we're starting with. So remember, for both of these, we want to create the exponential function that is modeled by this situation there, that this situation kind of lends itself to. So if we remember, again, I'm changing to t instead of x just because we're dealing with time in both these situations. This is what we're looking for. We need our y-intercept and our base multiplier. Our base multiplier is found using our rate of change idea, and that we can see is given in the 6% and 7.6%. The y-intercept, what's another word for y-intercept? Another way to think about it, especially when we're dealing with a context. That's right, the starting value, right? So this is our starting value. So for both of these functions, it's really easy to figure out our starting value because it's given to us directly in each problem. So here we have some value after an amount of time. So I'm going to use the function v of t. So this is the value after t, and since it's annually, that's years. So v of t is equal to, our initial amount is the 4,545. Now, in this we don't need to add the zeros, and we definitely don't want the dollar sign. We just want the number itself. And now, if you have a number with 0.00000, whatever, you're not putting those zeros in there, you just have the whole number. Now, what is b? Well, first we have to figure out is, are we increasing, like exponential growth, or are we decreasing, like exponential decay? That's going to tell us whether I need to kind of add to 1 or subtract from 1 by percent. And since it says we are increasing, so our function is growing, then our 6% needs to be added to 1. Because we need to keep the 100% that we had initially, and we add 6%. So we convert 6% to a decimal, which is 0.06, and add it to 1. And that's it. There's our function. Our next one here. Okay, we have some amount after a time t. Our initial amount is 132. Now this is decaying at 7.6% hourly. So that means our t represents an hour. So every 1 hour, that t goes up 1. Now because we're decaying, we don't want to add this percentage to 1 because that would make us growing, and that's not what we want. So we need to subtract from 1. And so if you're ever like, I don't know, should I add it to 1 or should I subtract it from 1? I'm not sure which one I should do. Just think, if I subtract it from 1, it's going to be smaller than 1, and therefore it's going to be decaying. So if your problem is increasing and you have a number here that would be exponential decay, you know that something went wrong. Okay? So since we're decaying, I want to do 1 minus 0.076 to subtract my 7.6%. And so what I'm doing is I'm finding what percent, essentially, I retain each time. And that is 0.924. And that's it. That's all we have to do. Okay? Now, some questions with this that could go along with either of these two things could be very simple, like what amount is left after a day? So then you would put t as 24 into your calculator and solve that for us, right? Those are all really easy things to do. Okay, now I want to show you guys a really cool trick. Let's do that. Let's actually do that real quick. Let's find what is a 24. So I want to find what amount is left after 1 day. Since 1 day is equal to 24 hours, that's where that's coming from. So how can I do this in my calculator? Well, I could easily type 132 times 0.924 raised to the 24th. Totally works. But I want to show you guys another way to do this. So grab your calculator. Okay, and I want you to go to this y equals menu. It's going to take you to something like this, right? This is where we did stat plots, we've done things like that. I want to type in this equation. Okay, so we type 132 times 0.924 raised to the x. Now remember, to get that x, you just use this little button right here for the x. And so it should get something that looking like this. We go down. I'm just going to hit enter. Now what I want to do is I want to use my table for this. Now what we need to do is we need to set up our table the way we want it. And if you look above this button here that says window, you see TBLSET, and that stands for table setup. So if I go to that, what I want to do is I want to take this independent which if you haven't never done this, it should look like this. And I want to highlight ask and hit enter. So that ask is highlighted. The reason why I want to do that is because then when I go to my table, which to get to the table, you just get second and graph, which you can see says table. It's empty, but I have y1. What's great about this is I can now put in any number I want for x, and it will give me my output. I don't have to scroll around, and if I want to do something like, what if I want to do like 3/7? I can do that in here. If I want to do 3/8, I can do that in here, right? It's really easy. And so I want to do 24, so I just hit 2 and 4, and you can see that is in my x's. Hit enter, and I can go up and highlight that if I want to get more. You can see there's 19.8 left. So that means that this thing that initially had 132 grams, that decays at 7.6% an hour, after 24 hours, will have 19.8 grams. And that's how we can do this. It's really easy. So the hardest thing with this is kind of understanding which one to use here, and then it's really just interpreting that problem. And that's just a really important to practice. Identify your independent and dependent variables, right? Your inputs and outputs and what they actually represent. Don't just say, oh, my input is T, my output is A, or my input is C, my output is V, right? Understand what these mean, right? My input is the number of years, and we're using T for that. The output is the value of this thing after T years. Down here, the input is T, which is the number of hours that have passed. And my output is A, which is the amount of this thing remaining. And so being able to kind of really understand that makes things a lot easier to do. Makes it a lot easier to go, okay, after one day, okay, well that means the time is 24 hours. And that goes in place of T because that's my time. And it doesn't make us set this equal to 24 because we're not setting the amount of 24. We are setting the time to 24. Any questions? Not that you can ask them right now. But if you do, send me a message. All right. Now, I want to go and talk about something called half-life. So, typically this is something used in chemistry, but it can be used in lots of things. So, half-life is the amount of time it takes to decay essentially in half. So what that means is, let's say we start with 100 and it takes 2 days to get down to 50. That means the half-life would be 2 days. And so this idea is something that we're going to do a lot of problems with, and we're going to kind of create a special little equation for, a little formula. And so what I want to talk about is a nice little problem. I want to write this up so you guys have it. The car tire initially had a tire pressure of 33 psi. So psi stands for pounds per square inch. Okay. A car tire initially had a tire pressure of 33 psi and has now sprung a leak. Sorry, I'm just looking at something else here. Okay. If it takes 20 minutes to lose half the pressure left in the tire create an equation for the tire pressure after t minutes. Okay, I'll get out of the way. Go ahead and pause this so you can write it down. All right, so we need to create an equation that can model the amount of tire pressure left in this. Now, first of all, is it even reasonable to think that a tire pressure would lose at a half or exponentially? And it is, because initially when the tire is full, there's a lot of pressure building up, and so when it springs a leak, it goes really quickly. Think about a balloon, right? If you open up the balloon, a lot of air rushes out quick, and then it kind of slows down as the pressure from the balloon is less. Same thing with the tire. Now, is it exactly exponential? Not necessarily, and it depends on the hole and a lot of other factors. But we're going to suspend that realism for right now. We're going to deal with the situation as it's presented to us. So what I know is that I initially have 33 psi. So the pressure in the tire after t minutes, we know it starts with 33. And so here's where this gets weird and tricky in the equation. And so we're going to kind of build this up here, and then we'll give a general half-life equation. Okay? So I know that after 20 minutes, I should be cut in half. So if t is 20, I need to multiply 33 by half. So what I can actually do is I can do this. I can multiply this by a half. Okay? But I don't want to just have t up there, because this wouldn't work. Because then if t is 1, cut it in half. And so t is minutes, not t is 20 minutes. So if t is 2, that'd be 40. That's not what we're doing. So when t is 20, I need this exponent to be a 1. So how can I make a 20 into a 1? Well, I can make it into a 1 by dividing by 20. So what this does is it makes it so that after 20 minutes, so when t is 20, 33 times 1 half to the 20 over 20. 20 over 20 is 1, 1 half to the 1 is 1 half, and we get 33 times a half. And so that's how we can create this equation. And so let's go through and give a nice general half-life formula. Okay? If the half-life something is k units, and it starts with an amount of A, okay? So this is our initial amount here, and K is the number of half-lives. So in our previous problem, the A here would be the initial 33 psi that we have in the tire. The K would be the 20 minutes, okay? So with an initial amount A, we can use the following half-life formula. We have A, T, so this is the amount of the thing we have after time T is equal to the initial amount we had. I'll underline that, that's our A. Not just the letter A as in we're talking. Times 1/2 to the T over K. And this will work all the time. It's really an easy thing to do. And it allows us to work with some really crazy and cool things. This formula here is our half-life formula. Again, if you write very few notes, you need to have this one written down. This is a one that you will need. I can guarantee you I'm going to give you a half-life problem on a test. So, let's do a problem with this. How many of you guys have ever seen a dinosaur movie or know of dinosaurs or anything like that? Well, if you're at home and you're raising your hand, that's silly. Why are you doing that? I can't see you. But awesome job. There's a thing with fossils and archaeology and lots of other things as well, but archaeology is one of the big areas, where they do something called carbon dating. And so what that is doing is it's using the amount of carbon that we know to be in organic life forms, so organic like us and carbon-based life forms. We kind of know roughly how much carbon is in those things, so like the bones of a dinosaur. And so by checking that fossil and looking at how much carbon is left in it, we can actually assess how old that fossil is using half-life. Using this mathematic that you are going to learn right now, you could tell how old a fossil was with two pieces of information. How much it normally would start with and how much it has at that moment. So specifically, we use the element carbon-14. Now, the 14 is not a number relative to our mathematics that we're dealing with. The 14 is just a naming system in chemistry. I believe, if I'm right, it has to do with the number of electrons that element of carbon has. And so that's something that, if you're a chemist and I'm wrong, don't persecute me, that's what that's for. So carbon-14 has a half-life of about 5,730 years. Okay, so if a sample, or we'll say if a fossil initially has so if a fossil initially has, we'll say 100 milligrams of carbon-14, create a model for the amount of carbon-14 left after t years, and find how much is left after 20,000 years. This is a pretty typical problem. This is definitely something that you could see on a test, in the homework, or just in your daily archaeological lives. So, let's first create our model. So, we need two things. We need to know, so for half-life, we need two things. We need to know the initial amount and the half-life. Because our formula was the initial amount times 1/2 to the t over k, where k was our half-life. So here, we can simply say that the amount of carbon-14 after t years, we need to know the initial amount, which is 100 milligrams, times 1/2 to the t over the half-life. That's it. That's all we have to do. Let me write that a little bit lower so I can write it a little bigger, make it very clear. There's our formula. That's all we have to do. We just plug those things into that equation and we're done. Now, our next part is simply to find out how much is left after 20,000 years. So we are trying to find A of 20,000. And of course, you guys are going to do that by hand. It's a super easy problem. You should be able to do the mental math and just know what it is, right? No. Calculators. So the best way to do this, unless you're doing a lot of things, unless you're going to use this equation over and over and over, it doesn't really make sense to put it into the table. I mean, you can absolutely if you want, but I'm just going to type it in at once. And when you do that, you just want to type it all in. So we want to type 100 times parenthesis 1 divided by 2. So we get that whole half, and then use our exponent button. Now again, depending on what type of exponent you have, if it's the one that I have, then you're just going to be able to type the division, no problem. If it's the one that just on your screen, it just has a little arrow thing, you're going to want to put parentheses around it. So we have 20,000. So in the exponent, we have 20,000 divided by 5,730. So it should look roughly something like this. And then hit enter. Bam. So after 20,000 years, we should have about 8.9 milligrams. Now, is that accurate? Is that right? Let's think about this. 20,000 years. So let's just round this to 5,000. It's a little more, but that's okay. 20,000 years, 5,000 goes in there 4 times. So that means that 20,000 years, because this is a little more than 5,000, is 3 full half-lives, and then a little bit more. So we can just say, okay, well, what is 1/2 to the third? And that's 0.125. And if I use math and change that to a fraction, I get 1/8. Okay. If I do it a fourth, so I get 0.0625. So if I were to go to all the way to 4 half-lives, I'd be at 0.0625. So 3 half-lives, which we've gone more than, is 12.5. 4 half-lives, which haven't gone that far, is 6.25. So we're somewhere in the middle, which makes sense for where we're at with our half-lives. That's it with half-lives, guys. I hope this makes sense to you guys. The last thing I want to do is some regression. I'm not going to do a problem with regression because it's exactly the same as the linear regression you guys have already done. Hopefully that would make sense. If it didn't make sense, you need to be messaging me and talking to me and getting help on that, because that was last week. You should have had that done. So I just want to make a quick note. When you're doing exponential regression, remember, stat and then edit. You're going to put your values into L1 and L2 here. Okay, I already have mine in there. That's just a random list from a different problem, and it gave me this thing right here. Now, if I want to do exponential regression, I want to go stat, go over to calc, and we scroll down. It should be option 0, EXP regression. And it's doing its thing, and we get this. So it gives us the equation that y equals a times b to the x. A is 0.554, b is 1.8. So let's throw that into my 0.554 times 1.8 to the x. So if I throw that in here and I hit graph, see, there's my points, and there's my exponential function coming through them. Now that's not a great fit, and that's okay. Depending on the problem, you may or may not have a good fit. But it's really simple, right? So make sure the only difference between doing exponential regression and linear regression and any other regression is the option you choose when you hit stat, then go over to calc, and which option you choose there. Okay? You do everything the exact same. The stat plot is still the exact same. Entering your information is still the exact same. The only difference is instead of going down and choosing option number 4 under the stat calculate, you go all the way down to option, I believe 0 was the one for exponential regression. That's it, you guys. That's the end of chapter 2. I hope you guys learned something, and I hope you guys are working through those problems. And I'll see you guys later with chapter 3.